Hi, the purpose of this video is to give some practice and examples in determining the sign of delta G or delta G prime and delta G naught prime. And so delta G prime is simply the free energy change of a reaction at neutral pH. That's what this little prime symbol means. And delta G naught prime is the standard free energy change, which is the free energy change of a reaction under standard conditions. And under standard conditions, all reactants and products are present continuously at 1 molar. And so in all cases, when we're trying to determine the sign of delta G prime or delta G naught prime, what we want to do is compare the concentrations of products and reactants that are present at a given moment, those are the prevailing concentrations, to the ratio of product to reactant when the reaction has reached equilibrium, and that is the equilibrium constant, or KEQ or K prime EQ. Now remember, this prime just refers to a pH of 7, a neutral pH, and we typically don't need to worry about it in our calculations. Sometimes you'll see this prime here, sometimes you won't. The key thing is when you see this little circle here, when you see delta G naught prime, your mind needs to automatically click and realize that we're looking at standard conditions. Standard conditions are simply a set of conditions the scientists have devised to be able to compare the energetics of reactions. And so standard conditions include temperature of 25 degrees Celsius, pressure of 1 atmosphere, pH of 7.0, and what's most relevant for our purposes, products and reactants are continuously present at 1 molar. As soon as you see this symbol, you need to know our current concentrations of products and reactants are 1 molar. So let's look at a sample reaction. This is a reaction that is present in glycolysis, which is how we get energy out of glucose molecules. This is the conversion of a molecule called dihydroxyacetone phosphate, we're going to now call this DHAP, to a molecule called glyceraldehyde 3-phosphate, we're going to call this GAP. So this conversion of DHAP to GAP is a reversible reaction. That's what this symbol here tells us. And for all reversible reactions, we can experimentally determine a value called the equilibrium constant. What this equilibrium constant tells us is the ratio of the product, which is always what's written on the right, to the reactant, which is always written on the left, when this reaction has reached equilibrium. So this reaction has an equilibrium constant of 22. What this means is when this reaction reaches equilibrium, our ratio of product to reactant, our ratio of glyceraldehyde 3-phosphate to dihydroxyacetone phosphate is going to be 22 to 1. When this reaction reaches equilibrium, there are going to be 22 molecules of GAP for every 1 molecule of DHAP. And so what can this tell us about the energetics of this reaction? Well, what this tells us is beginning with DHAP and GAP at any concentrations, a reaction will proceed spontaneously in the direction that moves us closest to this ratio of GAP to DHAP. I also want you to remember what equilibrium does mean and doesn't mean. Equilibrium means there is no longer a net change in the concentration of products or reactants with time. Equilibrium does not mean that the concentration of reactants and products are equal to each other. Equilibrium also doesn't mean the reaction has stopped happening. In fact, when a reaction has reached equilibrium, the reaction is still occurring. But what is happening is the rate of the forward reaction equals the rate of the reverse reaction. And so, beginning with concentrations of DHAP or GAP at any levels, the reaction will proceed spontaneously, sometimes forward, sometimes reverse, net in the direction that will move us to this balance of 22 to 1 GAP to DHAP. Sometimes when I'll get the equilibrium constant, I will actually write out the equation, the chemical equation, and write the equilibrium values on top of the reactant so I can keep straight. When this reaction has reached equilibrium, we'll have 22 gaps for every 1 DHAP. And what I'm going to do here is I'm going to plot the amount of energy in our system at all possible ratios of gap to DHAP. So this is the concentration of gap and the concentration of DHAP under prevailing conditions. And we're going to see all possible ratios. As we move very far to the right, we have much more GAP than DHAP. This fraction is getting much bigger. As we move to the left, we have much more DHAP than GAP as this fraction gets smaller. And this system is at the lowest free energy, meaning the most stable when our reaction is at equilibrium. And so this value right here on the x-axis is the equilibrium constant for this reaction. It is the particular ratio of GAP to DHAP when this reaction is at equilibrium. And we already saw that that value is 22. So 22, the ratio of gap to DHAP, is the lowest free energy situation for this reaction. Now, suppose I told you that the concentration of DHAP was 1 micromolar and the concentration of gap was 7 micromolar. And I ask you, what is the sign of the free energy change of the forward reaction? So the first thing we're going to do is determine the ratio of product to reactant, of gap to DHAP under these particular prevailing conditions. And so the ratio of gap to DHAP is 7 micromolar gap to 1 micromolar DHAP. This cancels, the micromoles cancel to 7. And we now plot that value on this x-axis. So remember, 22 is our equilibrium constant, and our prevailing ratio of gap to DHAP is 7, over here to the left of the equilibrium constant. And we see that this represents a situation of much higher free energy than we had at equilibrium. And so the question is, what is the sign of delta G when we move forward? Well, when we move forward, beginning with a ratio of 7 gap per every 1 DHAP, when we move forward, meaning when we convert more DHAP to GAP, our ratio of GAP to DHAP is going to increase. We're going to be moving closer to equilibrium. So moving forward in this case is going to move our ratio of product to reactant closer to equilibrium. And the key concept behind all that we're going to be talking about today is that moving towards equilibrium is spontaneous, is exergonic, means has a negative delta G. And hopefully you can see that moving forward is moving our system into a lower free energy place. And so that is exergonic. Moving to a lower free energy place is exergonic negative delta G. Okay, so the delta G or delta G prime of the forward reaction had a negative sign. What is the sign of delta G prime of the reverse reaction? Well, we're going to come to that same spot where we had our ratio of 7 gap to DHAP. And if the forward reaction was moving us closer to equilibrium, then the reverse reaction must be moving us further from equilibrium. And if we're moving further from equilibrium, that means that our sign of delta G would be positive. And so moving in reverse, meaning converting GAP to DHAP, is going to reduce this value. As we convert some of our gap to DHAP, this 7 is going to shrink as we move some of these gaps to DHAP. We're going to be moving further from equilibrium. We're going to be climbing higher and higher in energy. Climbing in energy is a positive delta G. That is endergonic, non-spontaneous. And again, I just want to make sure we understand the importance of these values. A reaction that is moving towards equilibrium. So if we begin at this ratio of gap to DHAP and we move forward, we'd be moving towards equilibrium. And as we move towards equilibrium, energy will be released. So as an exergonic reaction happens, energy is released. That energy can theoretically be harnessed to power cellular work. That is, other endergonic reactions, reactions with a positive delta G. By contrast, reactions that have a positive delta G, these cannot happen spontaneously. They can only happen if we put in energy to the system. So beginning at this ratio of gap to DHAP, 7:1, the only way we could move in reverse, moving GAPs into DHAPs, is if we put in energy. We'd need some other exergonic reaction powering this endergonic climbing up the hill. Here is another way to answer that same question. Given that our equilibrium constant is 22, meaning 22 gaps for every 1 DHAP when this reaction has reached equilibrium, what we could also do is just write down here our prevailing concentrations. So if we have 7 micromolar gap, 1 micromolar DHAP, hopefully we can look at these two and determine which direction, forward or reverse, will move these concentrations closer to the equilibrium balance. And so hopefully you can see that this forward reaction, converting some of this DHAP into GAP, is actually moving us closer to equilibrium. As we convert DHAP to GAP, we're going to get closer to that 22:1 balance. And so moving closer to equilibrium is exergonic, and that tells us that the free energy change, delta G or delta G prime, will be negative. Conversely, moving some gap into DHAP would be moving against equilibrium, going away from this 22:1 ratio. And so if we're going against equilibrium, moving further from equilibrium, this would require an input of energy, and so delta G or delta G prime would be positive. Here's another question. What is the sign of the standard free energy change of the forward reaction? Now, some people will read this question and say, wait, I thought you already asked this question up here, where you said, what is the sign of the free energy change of the forward reaction? The key thing you need to be able to recognize is this little circle right here. This is delta G not prime. This is the standard free energy change. The standard free energy change for a reaction assumes a specific set of concentrations of all reactants and products. No matter what reaction we're talking about, if you see this symbol, delta G not prime, or if you see the words standard, keyword standard free energy change, you need to remember that the reactants and products are both present at 1 molar. Therefore, our ratio of product to reactant under standard conditions is 1 molar over 1 molar, or 1. And so now this reduces to a question of what is the free energy change of the forward reaction when our ratio of product to reactant is 1. So here is that same plot we were just looking at. 22 is still the equilibrium constant. That hasn't changed. The 7 is from that previous question we were working on. But what we're going to plot now is our ratio of product to reactant under standard conditions. And that's right here. That's 1. And what we can see is this would represent a very high energy state for our system. And in fact, it should be clear that moving forward in this case, converting DHAP to GAP, is going to move us closer to equilibrium, closer to this low free energy state. So because moving forward is moving us closer to equilibrium, the standard free energy change of the forward reaction is negative. And we could draw this out the same way here, where again our equilibrium ratio is 22 GAPs to every 1 DHAP. We can write below our prevailing concentrations, which under standard conditions is 1 molar, 1 molar. And hopefully you can see that the direction that moves us closer to a balance of 22 gaps for every 1 DHAP is the forward direction. This is moving us closer to equilibrium, and so the standard free energy change for the forward reaction is negative. It's spontaneous. Energy is being released. That energy could, in theory, be harnessed to power an endergonic reaction. By contrast, the reverse reaction, converting some GAPs to DHAPs, is moving us away from equilibrium. We are piling up reactant when at equilibrium we have a domination of products. And so moving away from equilibrium is endergonic. And so the standard free energy change for the reverse reaction is positive. Let's do another example. Same reaction, same equilibrium constant. Now our concentrations are 2 micromolar DHAP and 80 micromolar GAP. And what is the sign of the free energy change of the forward reaction? Well, again, we're going to set up our ratio. Our ratio of product to reactant under these particular prevailing conditions is 80 micromolar over 2 micromolar, which equals 40. So we can find that here on our graph. This time we are going to be far to the right. This time our ratio of product to reactant, of GAP to DHAP, is greater than our equilibrium constant. And now we see that still we are at a very high energy level. So we are not at equilibrium, so that means we have higher energy in our system than we would if we were at equilibrium. But this time, if we moved forward, if we continue to convert DHAP into GAP, then this number would get bigger and bigger and bigger. As we convert DHAP into GAP, this 40 would start to climb into a bigger number. And so in this case, moving forward is moving away from equilibrium, and the free energy change, delta G prime, is positive. Here I'm asking, what is the sign of delta G prime of the reverse reaction, given these same concentrations? Well, in this case, converting GAP into DHAP, that's the reverse reaction, is going to be moving us closer to equilibrium. And so in this case, delta G prime will be negative because we're moving closer to equilibrium. And again, we can also solve this problem by comparing our concentrations to our equilibrium concentrations. Here we have 80 micromolar GAP, 2 micromolar DHAP. And hopefully you can see that the forward reaction converting DHAP into GAP is actually moving us further from equilibrium, further from this 22-to-1 balance. And so if we're moving further from equilibrium, that forward reaction has a positive delta G prime. The converse, the reverse reaction, is moving towards equilibrium. And so since this is moving towards equilibrium, converting GAP to DHAP is moving closer to this 22-to-1 balance, the delta G prime is negative. Okay, what is the sign of delta G naught prime of the forward reaction? Well, again, this is the exact same question we looked at just a minute or two ago. Again, as soon as you see this symbol, you need to remember we're talking about standard conditions, 1 molar product, 1 molar reactant. Our ratio is 1 molar equals 1. It's the exact same question we saw before. I'm just trying to make sure you recognize that as soon as you see this symbol, you are snapping from whatever concentrations I had given you to standard conditions. And so again, if the equilibrium constant is 22, under standard conditions, the forward reaction is moving us closer to equilibrium. One more. Suppose DHAP is present at 3 micromolar and GAP is present at 66 micromolar. What is the sign of the free energy change of the forward and reverse reactions? Again, we're doing the exact same thing every time. We're taking the ratio of product to reactant, of GAP to DHAP. 66 micromolar over 3 micromolar equals 22. Okay, this number sounds familiar. 22. Where is 22 on this x-axis? It's right here. 22 is our equilibrium constant. So when we have these particular concentrations, our ratio of product to reactant is already equal to the equilibrium constant. This means our reaction is already at equilibrium. This reaction is at the lowest free energy state it can possibly be. When a reaction is at equilibrium, there is no driving force for this reaction to occur in either direction. The delta G prime of the forward reaction is equal to 0. The delta G prime of the reverse reaction is equal to 0 because we are already at the most stable state possible. And we can draw our concentrations below our equation again, and hopefully you can see that this 3 micromolar DHAP and 66 micromolar GAP is the exact same ratio as 1 DHAP for every 22 GAPs. Therefore, we are already at equilibrium. The delta G prime for either direction is 0. There is no motivation for this reaction to occur in either direction. Just as a little footnote, remember, that doesn't mean this reaction has stopped happening. It just means the rate of the forward reaction equals the rate of the reverse reaction. There's no net change of product formation or reactant formation with time. Okay, let's look at a different reaction. Let's look at a reaction that we talked about in class, the conversion of glucose 6-phosphate to fructose 6-phosphate. This is a reversible reaction, and the equilibrium constant for this reaction is 1/2. And so what that means is when this reaction has reached equilibrium, at its most stable state, the ratio of product, F6P, to reactant, G6P, is 1/2. This means when we are at equilibrium, there are going to be 2 G6P molecules for every 1 F6P. Another way to say it, there will be half as many F6Ps as G6Ps when this reaction has reached equilibrium. It's important that you're able to articulate what this 1/2 means. If an equilibrium constant is 1/2, that means this reaction will proceed spontaneously in the direction that moves us closer to 1 product molecule for every 2 reactants, 1 F6P for every 2 G6Ps. So suppose that G6P is present at 10 times 10 to the minus 6 molar, and F6P is present at 1 times 10 to the minus 6 molar. What is the sign of delta G prime of the forward and reverse directions for this reaction? Well, let's take the ratio under prevailing conditions. Our ratio of product to reactant is 1 times 10 to the minus 6 molar over 10 times 10 to the 6th molar. This reduces to 1/10. We're going to plot that 1/10 on the x-axis. So really this boils down to being able to compare fractions to each other. So 1/10 is going to be far to the left of 1/2. Our system is at a higher free energy place than it would be if we were at equilibrium. And hopefully you can see that the forward direction is going to move us lower in free energy as we move towards equilibrium. Therefore, delta G prime is negative. As we convert G6Ps into F6Ps, okay, some of these G6Ps into F6Ps, this value is going to get bigger and we're going to move closer to equilibrium. Conversely, the reverse reaction, converting F6Ps to G6Ps, would make our fractions smaller. And as we do so, we'd be climbing in energy, moving further from equilibrium. Therefore, delta G prime for the reverse reaction would be positive. Okay, let's look at another example. Suppose G6P is present at 8 micromolar and F6P is present at 12 micromolar. What is the sign of delta G prime of the forward and reverse reactions? Again, we're doing the exact same thing, taking the ratio of product to reactant under these prevailing conditions and comparing them to our equilibrium constant. So our product to reactant, F6P to G6P, is 12 micromolar over 8 micromolar, which equals 1.5. That is going to show up far to the right here on this x-axis. It is greater than our equilibrium constant. And so our system is at a higher free energy than it would be if it were at equilibrium. And if we were to continue to move forward, meaning convert G6P to F6P, convert G6P to F6P, if we were to take some of this 8 and move it to the top of this fraction, this number is going to get bigger, and we're going to move further from equilibrium, climbing in free energy. So the forward reaction, delta G prime, has a positive sign. Therefore, the delta G prime, the free energy change of the reverse reaction, will have a negative sign, because going in reverse, converting some of this F6P to G6P, will move us closer to equilibrium, to this 1/2 ratio. Okay, suppose G6P is present at 4 molar, F6P at 2 molar. What is the sign of delta G prime of the forward and reverse reactions? Let's take our ratios. F6P over G6P, under prevailing conditions, 2 molar over 4 molar, this reduces to 1/2. This number sounds familiar. Let's find it on the x-axis. 1/2 is our equilibrium constant. So under these conditions right here, our reaction is already at equilibrium. It is at the lowest free energy state it can possibly be. Therefore, a reaction that is at equilibrium, the delta G prime for the forward and reverse reaction equals 0. There's no driving force for this reaction to occur in either direction. Finally, what is the standard free energy change for the forward reaction? Now, as soon as you see this symbol, you need to think standard conditions. 1 molar F6P, 1 molar G6P. Our prevailing ratio then is 1. And we need to find 1 on this x-axis. 1 is over here. When 1 is greater than our equilibrium constant, the forward reaction will be moving us further from equilibrium under standard conditions. Therefore, the standard free energy change of the forward reaction is positive. Now, for all of these, we can do the exact same thing we did before, where we compare the equilibrium ratio on top of the chemical equation to the different prevailing ratios. So over here on this first problem, we can draw our concentrations of G6P to F6P. This is our 10 times 10 to the minus 6 molar and our 1 times 10 to the minus 6 molar, and figure out which direction would move this reaction closer to equilibrium. Well, the forward reaction is going to move this reaction closer to equilibrium. Therefore, delta G prime forward is negative, exergonic. By extension, the reverse reaction must be endergonic, requiring an input of energy, positive delta G. For this example down here, where we had 8 micromolar G6P and 12 micromolar F6P, hopefully you can see that converting some of this F6P into G6P will move us closer to a 2-to-1 ratio of G6P to F6P. In this case, our reverse reaction will be spontaneous, negative delta G prime, and our forward reaction will be moving away from equilibrium, would have a positive delta G prime. Then if we drew these numbers in, 4 molar, 2 molar, well, this is equal to this balance of 1 F6P to 2 G6P. Therefore, this reaction is already at equilibrium. The delta G prime for forward and reverse reactions is 0. And then finally, we can map our standard for energy change on this list. 1 molar product, 1 molar reactant. Hopefully you can see that the direction that would move us closer to equilibrium is the reverse direction. beginning with equal concentrations, product and reactant, we'd have to go in reverse to get twice as much reactant as product. And so the reverse reaction would have a negative standard free energy change, and the forward reaction would have a positive standard free energy change. And so all of these values are the same as what we determined when we were comparing the ratios of product to reactant under prevailing conditions to the equilibrium constant. So hopefully after watching this video, after reviewing your notes, after doing the assignment, you feel more confident in being able to predict the sign of delta G prime or the standard free energy change of a reaction by comparing the prevailing ratio of product to reactant to the equilibrium constant, which is the ratio of product to reactant when this reaction has reached equilibrium. And if you're struggling, I encourage you to go back to the beginning of this video, write down everything that I'm writing, work through it again. You might have to work through it a couple times, but this is the kind of thing that requires practice in manipulating the numbers, drawing the graphs, comparing fractions. Try to come up with some different values and see if you can predict, come up with different concentrations and see if you can predict the sign of delta G given new sets of prevailing concentrations.